Hello students, welcome back to this lecture series of M.Sc. part 1. In this lecture we are going to discuss Lagueer functions. So these Lagueer functions generally use or specify the basis state in the quantum mechanics. So we know the general form mathematical expressions of these Lagueer functions, that is x into t square y by dx square plus 1 minus x into dy by dx plus n into y is equal to 0. This is a mathematical expressions. So of this Lagueer differential equations, also we can write like this: d square y by dx square plus 1 minus x into dy by dx plus n into y by x n by x into y is equal to 0. Okay, so from these differential equations we easily observe the singularity of this differential equations. Okay, so x is equal to 0, it is a regular singularity of this differential equations. Okay, because this 1 minus x divided by x and the n by x, this is a finite things when the x approach to 0. Okay, so this is a regular singularity of this differential equation x is equal to 0. Okay, so here we are going to try to solve this differential equations in the term of the power series. Okay, so for that here we are going to assume the one solutions in the term of the power series, that is y is equal to summations k is equal to 0 to infinity a k x power m plus k. Okay, this is a series solutions. Or also we know the, if I expand, or so it is a naught x power m plus a1 x power m plus 1 plus a2 x power m plus 2 and so on. Okay, so from this we can find dy by the dx, that is dy by dx is equal to summations over k is equal to 0 to infinity m plus k into ak x power m plus k. Okay, and the d square y by dx square is equal to summations over k is equal to 0 to infinity m plus, sorry, here is a minus 1, m plus k into m plus k minus 1 ak x power m plus k minus 2. Okay, so we have the now expression for the y dy by dx and the d square y by the dx square. Okay, so this thing we are going to substitute here, d square y by the dx square and the dy by the dx and the y. Okay, or in this equation. Okay, so x into d square y by the dx square, that is k is equal to 0 to infinity m plus k into m plus k minus 1 ak x power m plus k minus 2. Okay, this is the first terms, and the plus 1 minus x, so 1 minus x summations our k is equal to 0 to infinity dy by the dx, it is ak m plus k into x power m plus k minus 1, and the last term, that is plus n into y, so n into y, that is k is equal to 0 to infinity ak m x power m plus k is equal to 0. Okay, so this is we have the expressions for the in the term of the series for the Lagueer differential equations. Okay, so if I simplify this thing, so it is summations k is equal to 0 to infinity m plus k into m plus k minus 1 x power m plus k minus 1. Okay, this minus 2 and here is a plus 1 will be cancelled out. Okay, so remain is 1 x power m plus k minus 1. Okay, plus summations k is equal to 0 to infinity ak into m plus k x power m plus k minus 1. Okay, multiply here multiply this summation to this bracket. So first term is these things and the plus second one, that is summations k is equal to 0 to infinity, that is x into x power m plus k minus 1. So here summation ak m plus k x power m plus k. Okay, and the last term, that is n into summations k is equal to 0 to infinity ak x power m plus k. Sorry, here is a minus sign. Okay, this one, so t is equal to 0. Okay, so now take out this common, that is x power m plus k minus 1 and the x power m plus k. Okay, it is like summations k is equal to 0 to infinity ak m plus k into m plus k minus 1 plus m plus k into x power m plus k minus 1 and the minus. Okay, this is for the m plus k, this is for the this term. Okay, now second, okay, take out the minus is common from these two summations. Okay, so minus is common into ak m plus k minus n into x power m plus k is equal to 0. Okay, so here is this n, it's minus, we take out this minus is common. Okay, so that's why here is a minus sign. Okay, so now from these first summations we can take out the common, that is m plus k. Just simplify this coefficients of the x power m plus k minus 1. So it is like this, k is equal to 0 to infinity ak into m plus k m plus k. Okay, x power m plus k minus 1 and so this m plus k into m plus k we can write like this, m plus k bracket square and the x power m plus k minus 1. Okay, and the plus minus summations k is equal to 0 to infinity ak into m plus k minus n into x power m plus k is equal to 0. Okay, so this is what we need. Okay, so from this here is now total two summation, first summation and the second summations. Okay, so we are going to find indicial equations from this expressions. So for the indicial equations we try to find the lowest degree terms. Okay, so we know the lowest degree term, if observe the first summations, the lowest degree term is x power m minus 1. So for that we need to put the k is equal to 0. Okay, in the first summation. So if I put the k is equal to 0 in the first summations, so we get n odd m square. Okay, so this coefficients of this x power m minus k, okay, so that equate it is equal to 0. Okay, so this is the indicial equations and from the initial equations, again here the a is not is equal to 0 and this m is equal to 0. Okay, so here we get the value of the m is equal to 0. Okay, and also we can put the k in the second summations. We can't put the k is equal to minus 1s, okay, because k is always positives. Okay, for the lowest degree terms. Okay, so in the next step, if I put the k is equal to k minus 1s, in the first summations, sorry, k is equal to k plus 1s, k is replaced with the k plus 1s, then we get that degree terms, that is x power m plus k in the first summations. Okay, so these things I put, then after putting in the first summations, k replaced with the k plus 1, and in the second summations, okay, k is equal to k. Okay, so we get the relation like this: a k plus 1, and equate the coefficients of these things is equal to 0. Okay, so we get the relation a k plus 1 into m plus k plus 1 bracket square and minus ak into m plus k minus n is equal to 0. Okay, these relations we get after putting the k is equal to k plus 1 in the first summation and k in the second summations. So from this we can find the recurrence relation, that is a k plus 1 is equal to m plus k minus n divided by m plus k plus 1 bracket square, okay, into ak. Okay, so this is recurrence relations, and here is a case, that is a naught is not is equal to 0 and the m is equal to 0. Okay, so by using these two relations we are going to find the terms, that is a naught, a1, a2, a3, like that. Okay, so if I put in this relation, that is a k plus 1 is equal to, in this if I put this m is equal to 0, okay, then this relations becomes k minus n divided by k plus 1 bracket square ak. Okay, after just using the a naught is equal to 0 and m is equal to 0, this is the case. Okay, so now if I put the k is equal to 0, then this relations becomes, that is a1 is equal to minus n divided by 1 and the a naught. And if k is equal to 1, so it is a2 is equal to 1 minus n divided by 2 square. Okay, so it is equal to 4. So 4 we can write 2 factorial into 2 factorials. Okay, and this ak, that is a1. Okay, so we a1 replace with the minus n into a naught. Okay, so it is minus n into a naught. Okay, so this 1 minus n we can write, if we take out the minus is common from this bracket, so it is minus into n minus 1. Okay, so this minus and the from this bracket what we take out the commons, that multiplies, so it is plus. Okay, so these total things we can write like this: n into n minus 1 divided by 2 factorials square into a naught. Okay, so that is a2. Now if I write for the k is equal to 2, so it is a3 is equal to 2 minus n. Similarly here also we can write minus n minus 2 divided by, so ak, okay, so 9 here, so it is 9, we can write the 3 okay, 9 into a2. Okay, so this a2 we replace with this expression, that is n into n minus 1 divided by 2 factorials bracket squares. Okay, so it is n into n minus 1 divided by 2 factorial bracket square, or also we can write the 4 factorials, sorry 4. Okay, so 4 into 9 36, so these things we can write total expression, that is 3 factorials square, and here is a naught. Okay, so a3 becomes minus 1, okay, power 3 n into n minus 1 into n minus 2 divided by 3 factorials bracket square a naught. Okay, so we have the now a1s, a2, a3 and the a naught. Okay, so this series we can write like this. Okay, so what we assume the series for this differential equation, that is y is equal to summations k is equal to 0 to infinity ak x power m plus k, but here m is already is equal to 0. Okay, so here we consider this x power k only. Okay, so this series, that is a naught x power naught plus a1 x power 1 plus a2 x power 2 and so on. Okay, so if I put the a naught and the x power naught is equal to 1, and the a1 that is minus n into a naught to x, and the a2 that is plus n into n minus 1 divided by 2 factorials bracket square a naught and the x square, and the plus a3, so it is minus, okay, and n into n minus 1 into n minus 2 divided by 3 factorial square to a naught x cube. Okay, and so on. So this is series solutions of these differential equations. Okay, so from this we can take out the commons, that is a naught, and this a naught, if it is n factorials, then we can call this expressions, mathematical expressions, that is Lagueer polynomials. Okay, so y is equal to a naught into 1 minus nx plus n into n minus 1 divided by 2 factorial square x square minus n into n minus 1 into n minus 2 divided by 3 factorial square x cube, and generally we can write minus 1 power k into n minus 1 into n minus 2 to n minus k plus 1, okay, and here is the ki factorial square x power k. Okay, so this is general expression for the Lagueer differential equations, sorry, solution of the Lagueer differential equations. Now this a naught, if I write it is equal to n factorials, okay, then this expressions is called Lagueer polynomials of these differential equations. Okay, so okay, we are stop here, we will discuss in the next lecture.